So these chemicals, these pollutants, can cause a variety of health problems. And because of that, the EPA has classified these specific ones that are damaging to health as hazardous air pollutants. This is a special category of toxins that are closely monitored by the EPA because they are particularly dangerous to our health. In other words, these hazardous air pollutants, or HAPs, cause cancer, they inflict nerve damage, they disrupt hormone function, and even fetal development. These are substances that are persistent in the ecosystem for a long time and therefore can accumulate in animal or human tissues. Most of these HAP chemicals are either metal compounds, chlorinated hydrocarbons, or volatile organic compounds that we talked about before. This includes things like gasoline vapors, solvents, and components of plastic. All of those are HAPs that you encounter on a daily basis. Most of these HAPs are emitted by chemical processing factories, things that produce gasoline, plastics, solvents, pharmaceuticals, and other organic compounds. Benzene, toluene, xylene, and other volatile organic compounds are among those. And dioxins, or carbon-based compounds containing chlorine, are released mainly by burning plastics and medical waste that contain chlorine. This is so bad that the EPA reports that 100 million Americans, in other words, 1/3 of the US, live in areas where the cancer rate from HAPs is 10 times the normally accepted standard for action. It is wild. So to put all of that into perspective and to understand what communities are the most vulnerable and most impacted by HAPs, I'd like you to do these online readings. The first one is put out by the Century Foundation, and it's called Environmental Racism Has Left Black Communities Especially Vulnerable to COVID-19. And there's also an environmental justice fact sheet put out by a group at the University of Michigan. So after reading those and perhaps watching that YouTube video that I mentioned before, I would like you to write a 2-paragraph reflection that will be included in your Unit 3 reflection. So when you're doing these readings, I want you to take notes on what surprises you or not and why. And focus on 2 or 3 facts that you've not heard about before and pay close attention to how these make you feel. Then think about specific actions that should be taken to change the existing pattern. And also ask yourself, who has the power to enact substantive change? So there's a group called the Toxic Release Inventory, and it was established in 1986 to help inform communities about toxic substances that are produced and handled in their area. These are self-reported statistics from about 23,000 factories, refineries, mines, power plants, and chemical manufacturers, all in an effort to report on toxic releases above a certain amount. And this will help inform waste management methods for about 667 toxic chemicals. Companies that produce more than 25,000 pounds or handle more than 10,000 pounds of a listed toxic chemical must report it to the Toxic Release Inventory. And in that fact sheet that I mentioned on the previous page, it says, on average, people of color comprise 56% of the population living in neighborhoods with those TRI facilities, compared to 30% elsewhere. So now let's switch gears and focus on a case study that really first shined a light on the health impacts of air pollution. This is the case study of the Great London Smog.
London is famously foggy. Sometimes that can mean a wistful stroll or another excuse for a cup of tea, but when fog mixes with the smoke and chemicals produced by industry, it becomes something new: smog. And for a couple of centuries, London's smog could kill. Really bad smogs could kill 1,000 people in a few days, but no one did much about it until 1952, when a 5-day smog in London killed an estimated 12,000 people. It was called the Great Smog of London, and it helped wake up the country and the world to the dangers of unrestricted pollution. Fog is just a cloud that forms down here on the ground, which by itself isn't that bad. You might not be able to see well when you're driving. You might not be able to land your plane, but it's nice. But clouds can act like sponges, forming around and trapping whatever's already in the air. This wasn't the problem until the 1200s, when a lot of London switched from wood to coal for heating their homes. Burning coal creates soot and smoke, which can irritate your lungs, and also creates poisons like sulfur dioxide and carbon monoxide. Sulfur dioxide, which is a sulfur atom bonded to 2 oxygen atoms, reacts with water to form sulfuric acid, which can harm your internal organs, as you might imagine. And carbon monoxide, which is 1 carbon and 1 oxygen, binds with the hemoglobin in your blood to stop oxygen from getting around your body. So when London started burning coal, all the smoke and chemicals mixed with the natural fog, and it became thicker and darker as years passed. It wasn't a health crisis at first, but people did complain that the smoke smelled terrible. And this was back in the 1200s, when everything smelled terrible already. But it was easier to keep burning coal than to switch back to wood, so for centuries they just accepted the occasional thick, dark, smelly cloud hanging over the city. As you do. Things really got dangerous when the Industrial Revolution happened in the 1700s, because now coal wasn't just heating homes, it powered huge factories throughout the city, and all that extra smoke and soot made the air in London's fogs much darker. It became so common that a physician named Harold Antoine Deveau invented the term smog to describe it. Really smoggy days completely blacked out the center of the city so that you couldn't see more than a few meters ahead of you, even in the middle of the day. The soot also irritated people's lungs, causing illnesses like bronchitis to become more common. Some people even suffocated from breathing so much smoke or the poisons in the air. Individual smogs in 1873 and 1892 each killed over 1,000 humans and livestock, and we don't even know how many people died early from collecting soot in their lungs over the course of their lives. But coal kept London flourishing, so nobody did anything to stop it. Then came the Great Smog. On December 5th, 1952, a thick fog rolled in and mixed with London's dirty air, just like it did most winters. But this time, high-pressure weather systems surrounded London, allowed for moving on. So an especially dense black smog stopped on London for 5 miserable days. The smog was so thick that flights were grounded, most public transportation was canceled, trains collided, and theaters and movies stopped because people couldn't see what they were watching. This is difficult to imagine. This was 1952. Not that long ago. An estimated 4,000 people died in those 5 awful days before the smog dissipated. A lot of them suffocated because their lungs were inflamed from breathing in so much soot. And with sulfur dioxide from the burning coal reacting with water vapor in the smog, Londoners also spent those 5 days breathing air full of sulfuric acid. That and the smoke contributed to respiratory and other health problems, which killed around another 8,000 people in the following months. Ultimately, roughly 1 in 1,000 Londoners died because of the Great Smog. Some people argued afterward that the spike in deaths was due to a flu epidemic, but scientists have investigated that in all sorts of ways, and it's really unlikely that the flu could have been anywhere near as devastating as the smog itself. 4 years later, Parliament finally passed a Clean Air Act that dictated what kinds of fuels could be burned within the city. It and other laws have helped rein in the smog problem in London, but even today, London's air pollution lowers the life expectancy of a lot of people and is indirectly linked to tens of thousands of early deaths every year throughout the United Kingdom. Despite the Great Smog's devastation, it took a while for other industrial powerhouses to take the hint. New York City had a series of smogs in the 1960s that affected more than 16 million people, and black soot-filled rain coated Boston around the same time. But eventually, lawmakers around the world stepped in. Starting in the 1970s, laws got serious about limiting pollution, forcing car companies to make more efficient engines and factories to produce fewer emissions. Because it turns out, turning air into poison, not a great idea. Thank you for watching this episode of SciShow. You're great. And a special thanks to all of our patrons on Patreon for making it happen.
So that was the Great London Fog of 1952. As was mentioned in the video, it was precipitated because everybody needed coal for their homes, but also because of the Industrial Revolution that required massive amounts of coal burning in those industrialized power plants. At the time, there were no air quality laws to prevent all of that buildup of soot and smog. And so for 4 days in 1952, a weather pattern that was called an inversion created the worst air ever experienced in that area. And this inversion is a reversal of the normal behavior of temperature in the troposphere, which we learned a couple of lectures ago is a region of the atmosphere that's nearest the Earth's surface. And this inversion had a layer of cool air at the surface be trapped full of pollutants because it was overlain by a layer of warmer air. This trapped pollutants at the surface and turned day into night with extremely decreased visibility. People are breathing in that nasty soot full of pollutants. Visibility in some areas was reduced to 1 foot in front of you. And overall, about 152,000 people got sick and over 12,000 died. So what is this temperature inversion? Atmospheric temperature inversions are a reversal of the normal behavior of temperature in the atmosphere, in which a layer of cool air at the surface is overlain by warmer air. These occur where ground level air cools more quickly than the upper atmosphere. With the cold air resting below the warmer air, we don't have any mixing, and the pollutants therefore are trapped near the ground. So here under normal conditions, we have increasing temperature with decreasing altitude, with cooler air at the top, cool air in the middle, and warm air at the surface. But when nighttime comes around, we have an inversion causing cooler air at the top, followed by warmer air in the middle that basically acts like a cap to the cool air below, trapping in all of those pollutants here. One of those pollutants is mercury, which is unfortunately a key neurotoxin. In other words, it can inflict nerve damage. Airborne metals originate mainly from the combustion of fuel, especially coal. And these contain traces of mercury as well as arsenic, cadmium, and other metals, as well as sulfur and other trace elements. Airborne mercury has received special attention because it is widespread and persistent neurotoxic capabilities. This is, in other words, a substance that damages the brain and the entire nervous system, even in minute doses. Minute doses of mercury and those other toxins can damage and provide other impairments, especially in young children and developing fetuses. About 70% of airborne mercury is released by coal burning power plants. Metal ore smelting and waste combustion also produces airborne mercury and other metals like cadmium. About 75% of human exposure to mercury comes from eating fish, believe it or not. And this is because aquatic bacteria are mainly responsible for converting airborne mercury into methyl mercury. And that methyl mercury is a form that can accumulate in living tissues like fish tissues. So this is why for many years, pregnant women were warned from eating too much raw fish or tuna because of the high concentrations of mercury that bioaccumulates in those fish. So air pollutants like mercury and arsenic can have the potential to travel the world. They can travel far. Dust and fine aerosols can be carried great distances by just the wind. Pollution from the Great Lakes and the Ohio River Valley contaminate the Canadian maritime provinces and can be traced as far as Ireland. Similarly, dust storms from China's Gobi and Taklamakan deserts routinely close schools, factories, and airports in Korea, Japan, and even Seattle in the United States. So dust storms in China have the potential to affect what's happening in the United States. In one particularly severe dust storm in the year 1998, chemical analysis showed that 75% of the particulate pollution in Seattle came from China. We can take a look at how bad the air pollution is today by accessing this website. It's waqi.info, and it tells you in a color-coded and quantitative way what the air quality is in that region. So going from good in green, moderate, and yellow, all the way to hazardous in this dark, deep purple, we see by and large that areas in Asia have this unhealthy, very unhealthy, or hazardous air quality. We can take a look at where we are, and we see that we're straddling good to moderate in the Southeast. So what does this long-range pollution transport mean? So in addition to transporting those particles to places like Seattle, where airports and flights might be disrupted, these pollutants also have the potential to wreak havoc in upper layers of the atmosphere, including destroying the ozone that's located in the stratosphere. So chemical reactions of atmospheric gases and pollution produce the phenomenon known as the ozone hole. This ozone hole is a thinning, it's not an actual hole, it's the thinning of the ozone concentrations in the stratosphere. This thinning was first discovered in 1985, but it probably started developing at least in the 1960s. And that's because these chlorine-based aerosols, such as CFCs or HCFCs, so CFC standing for chlorofluorohydrocarbon, and HCFC standing for hydrochlorofluorocarbons, those are the culprits and the principal agents behind ozone depletion. They are non-toxic, non-flammable, chemically inert, long-lasting, and cheaply produced, meaning that these compounds were ubiquitous, they were found everywhere, and they were extremely useful as industrial gases in refrigerators, air conditioners, styrofoam insulation, and aerosol spray cans like hairspray. And that persisted for years. From the 1930s until the 1980s, these CFCs were used all over the world and were widely distributed. So that means that excess went up into the atmosphere and it thinned out the ozone layer. Now, this ozone, as we mentioned previously, does a really good service for us because it prevents excessive UV radiation from coming down to the Earth's surface. If humans were exposed to too much UV radiation, this has the potential to cause cancer and reduce agricultural production and disrupt ecosystems. So preventing the thinning of the ozone layer is actually a high priority. And so the discovery of stratospheric ozone losses brought about a remarkably quick international response. This response included phasing out of those CFCs that were mandated by this 1987 Montreal Protocol. And this was the first of several major international agreements on phasing out most of CFCs by the year 2000. In addition, $500 million was established to assist poorer countries in switching to non-CFC technologies. And fortunately, at that time, there were alternatives to CFCs. They already existed. So it was actually a really quick and effective response. They immediately understood that, hey, what we're doing is working. We are no longer contributing to the thinning of the ozone. And so the deadline for the elimination of all CFCs was successfully moved up to 1996. So CFCs now are being removed from the atmosphere more rapidly than they are being added. And in 50 years or so, stratospheric ozone layers are expected to be back to normal. And we can clearly see that through time from 1982 through the year 2002, we saw a precipitous decrease in the concentration of these compounds in the atmosphere as measured in millions of tons. There's a YouTube video on the tartan for you to watch that describes the importance of the ozone and how we eventually set ourselves straight with the banning of CFCs. And so this shows what can happen when nearly all of the world's countries put their heads together and really try to solve these huge environmental problems.